Okay guys, in this video we're going to talk about the difference between molecular compounds and ionic compounds. And this is a very important distinction that you need to be able to make because a lot of other concepts in chemistry build upon this distinction, most notably chemical nomenclature. So we're going to define ionic and molecular compounds for you, and then we're going to make a prediction based on the periodic table whether or not we're dealing with a particular molecular compound or ionic compound. So you need to be able to look at a chemical formula, and based upon the position of the atoms within the compound, you need to be able to determine whether it's a molecular compound or an ionic compound. And we'll go through some examples of that. So compounds can be classified as being either molecular or ionic in nature. Molecular compounds are composed of identical molecules, and molecules are small, definite groups of atoms that are chemically bonded together by attractive covalent bonds. Okay, so their molecules are little tiny units, sometimes they're bigger, but they're small groups of atoms that are identical to one another. So the grouping is identical to one another for every given molecule. Nonmetals, when they get together with other nonmetals, they tend to form molecular compounds. Ionic compounds, on the other hand, are composed of ions, which are charged. And these ions are held together by electrostatic forces. So an ion is a charged atom, or it's a charged molecule. And typically, the types of elements that come together to form ionic compounds are when metals form compounds with nonmetals. So metals and nonmetals tend to form ionic compounds together. Nonmetals bonding to nonmetals tend to form molecular compounds. And I just want to show you quickly the periodic table. I think I've closed it. Let's open it back up again. Remember, metals are on the left-hand side of the metalloid staircase. Nonmetals are on the right-hand side. When you have nonmetals bonded to other nonmetals, it's a molecular compound. When you have metals bonded to nonmetals, it's an ionic compound. Okay, so this is a very important distinction that you need to be able to make. I can't overstate how important it is. So different types of molecular compounds. So first we'll start with molecular elements. Okay, so elements, you'll recall, are substances that are composed of only one type of atom, but elements can come in different forms. So some elements come as monoatomic species, such as the noble gases, helium and neon. They don't form bonds with anything, not even with themselves, and so we would call them monoatomic elements. Other elements will react with themselves, other atoms will react with themselves to form diatomic molecules. So for example, hydrogen and oxygen and nitrogen and the other and the halogens, they all come as diatomic molecules. Other species are polyatomic, for example, phosphorus and arsenic and sulfur. These form little molecules involving 4, 4, and 8 for these particular atoms. Sometimes you'll find polyatomic, you'll find extended structures. So metals, for example, they form metallic crystal structures, which we'll talk about in more detail later on in the course. So these are the different flavors of molecular elements that you'll find. I also need to define for you the term allotrope. So it turns out that elements can exist in more than one form. So for example, you could have, we have diatomic oxygen, but you could also have monoatomic oxygen as well. It does exist, And so that's a different form of oxygen. There's yet another form of oxygen called ozone, which consists of little triatomic molecules. So diatomic oxygen and monoatomic oxygen and triatomic oxygen are all allotropes of the same element. So an allotrope refers to the fact that an element can exist in more than one form. Carbon is another famous example of an element that has different allotropes. So for example, graphite, which you'll find in your pencils, is one form of carbon. Diamond is another form of carbon, and there's still other forms. So another form of carbon are these fullerene molecules, which look a little bit like a soccer ball in the sense that it consists of hexagons and pentagons that are all formed by carbon atoms. So these are all different allotropes of carbon. So on the next slide here, we're going to start talking about ionic compounds. So ionic compounds involve cations and anions. Protons and electrons are the source of charge within matter. Okay, and so an ion is a species that has an unequal number of protons and electrons. The cation has fewer electrons than it does protons, and so it's positively charged. Anions are negatively charged because they have more electrons than protons. Okay, so we have positively charged ions called cations and negatively charged ions called anions. And the ionic compound consists of both cations and anions. You can have monoatomic ions. That is, you have a single atom that has a non-zero charge. Metal atoms, when they form monoatomic ions, they tend to form cations, typically. So metal atoms usually lose electrons to form a positively charged cation. Non-metal atoms, on the other hand, they tend to gain electrons to form anions. Polyatomic ions are molecules that have an unequal number of protons and electrons, and so they're molecules that have a non-zero charge. In the next video on chemical nomenclature, we are going to learn how to name the different ions, and we're going to have a list of polyatomic ions that we have to memorize. For now, let's talk a little bit more about ionic compounds. So unlike molecular compounds, which form small definite groupings of atoms called molecules, ionic compounds consist of extended crystalline structures where you have cations and anions alternating in an extended structure that just goes on and on and on and repeats itself. And so the bonding within ionic compounds is based on electrostatic interactions between the cations and the anions. You may recall that the rule is for charges that opposites attract. So positive charges are attracted to negative charges. That is, cations will be attracted to anions. However, like charges repel one another. So cations are repelled by cations, and anions are repelled by anions. And so what you'll find in the ionic compound is that a given cation is going to be surrounded by anions, and every anion is going to be surrounded by cations. Overall, however, the ionic compound is neutral because you have an equal number of positive charges and negative charges, such that the charges all balance out. These attractive and repulsive interactions that I'm talking about are called Coulombic interactions, and they are what hold the extended crystalline structure together. Like I said, they expand throughout space. They are not discrete molecules, so ionic compounds are very different from molecular compounds in that sense. The term formula unit is a generic term used to describe either molecular compounds or ionic compounds. it refers to the smallest grouping of atoms or ions that is needed to represent the chemical formula of that particular substance. For molecular compounds, the smallest unit is a molecule, so the formula unit is equivalent to the molecule for a molecular compound. And we are going to learn how to write out different molecular formulas throughout this course. And the main rule for molecular compounds is that you never ever reduce the subscripts within the chemical formula for a molecular compound. To do so changes what compound you're talking about. For ionic compounds, on the other hand, since they form extended structures, there is no molecule. In fact, the smallest unit is what we call the ionic formula, and the ionic formula is the minimum number of ions that you need in order to balance the charge. So what's the lowest ratio of ions that will give you charge neutrality? And here's some examples. So for sodium chloride, we're going to learn that sodium ions form a +1 cation, and chloride ions form a -1 anion. And so the ratio is 1 to 1, and that balances the charge. In this iron 3 sulfate species, the sulfate is a polyatomic ion with a -2 charge, and the iron 3 is a +3 monoatomic cation. Okay, so you have an object that's got a +3 charge and an object that has a -2 charge. Well, you're going to need 2 +3s and 3 -2s in order to balance the charge. And so that's why the formula unit for iron 3 sulfate has these particular subscripts. And that's something that we're going to do some examples on to illustrate. I just wanted to point out that for ionic compounds, we often do reduce the subscripts, and we'll go through some examples. However, you need to do it with care. And so I'll come back to this example here and illustrate why we don't always reduce the subscripts in an ionic compound. So what I think I have for us next are some example problems, and so I'm going to go back to my paper here. So in part A, we're talking about chromium 3 oxide, which is a paint pigment. It's composed of chromium 3 ions and oxide ions, which have a -2 charge. So we've got these ions. And what we're being asked to do is to figure out what would be the formula for the chromium 3 oxide. Well, here's how you derive it. You start with your cations and your anions, and what I like to do is I like to bring the charges down and across to the other species. So these are going to become the subscripts in the chemical formula. So I'm going to write this as Cr2O3. Okay, and so this is the formula for chromium 3 oxide. And we can check the charge neutrality, right? You've got 2 + 3 cations, and you've got 3 -2 anions. Okay, so that's going to give you +6 -6, so you're going to get charge neutrality. Okay, so these subscripts are the minimum needed to give you charge neutrality. For part B, we can do the same thing. We've got strontium ions and oxide ions. We bring the charges down. Here, however, 2 to 2 is not the lowest whole number ratio. We can reduce this even further to 1 to 1. And so this is the correct ionic formula for the strontium oxide. Let's do another one. Let's do part C here. We've got potassium cations, and we've got a polyatomic ion, chromate. Here, the charge -2 applies to the entire species. Okay, we do the same thing. We can bring the subscripts down and across. So we would have K2 CrO4, and that would be +1. Whenever you have a +1, you omit it. Okay, so you wouldn't include, you wouldn't write it like this, however. This is not necessary. It's redundant. The way you write it would be K2 CrO4. In Part D, we're being asked to classify these different chemical formulas as to whether they correspond to an ionic compound or a molecular formula. And it may be helpful for you at this point to get out the periodic table. So I'm going to go ahead and grab that, and I'm going to squish it down a little bit. That should be good enough for us. So here you're facing all of these different chemical formulas. You need to be able to identify these compounds as being ionic or molecular. Okay, and the trick is to know the difference between a metal and a nonmetal, and whether and what types of elements combine to give you molecular compounds versus ionic compounds. So molecular compounds are formed between nonmetals. So when the atoms in your compound are all nonmetals, that indicates that you have a molecular compound. Contrast that with an ionic compound, where you will have a metal and a nonmetal, or you'll at least have a metal and a polyatomic anion. Okay, so we want to watch out for those. You can also have a polyatomic cation and paired up with any kind of anion as well. So there's some subtleties, but we'll tackle those as we get further into chemical nomenclature. Well, let's start with CH4. So carbon and hydrogen are both nonmetals. That means that CH4 is a molecular compound. Here we have diatomic bromine. Bromine is a nonmetal, so Br2 is a molecular compound. Calcium chloride. Calcium is a metal, chlorine is a nonmetal, so this is going to be an ionic compound. For the next one, we've got potassium metal, and then the NO3, that's actually one unit. This is the nitrate ion, as we will learn. And so this is going to be a cation and a polyatomic anion. We are going to recognize this as an ionic compound. Here, CH4O, these are all nonmetals. Okay, so there's no metals. So this is going to be a molecular compound. Lithium fluoride, lithium is a metal, fluorine is a nonmetal. So this is going to be an ionic compound. I think I wanted to go back and do this example here. So we have one more special example in the sodium oxalate species. So this is a metal, these are nonmetals, so this is an ionic compound. The rule is you're supposed to reduce the subscripts, but it's not correct to do it in this case because the anion is a polyatomic anion with a -2 charge, and the sodium is the cation. Now this polyatomic anion is a molecule, but it's a molecule that's charged, which makes it has extra electrons on it. So this is the anion. And the way you get to this formula is to take the -2 and put it down here, and you take the 1 and you put it there. Now it would be incorrect to reduce the subscripts in this case, because if you reduce the subscripts, you would get something like this, NaCO2. This is no longer the oxalate anion. It's something else. So this is not the same compound as that one. So you don't want to reduce your subscripts always for ionic compounds. You have to do it. You have to do it with care. You need to know your polyatomic anions, which we will get to in the next